Greetings, everyone. Welcome to a special edition of the AATRN Topological Complexity Seminar, held, I guess, in proximity to the AMS sectional, Southeastern sectional meeting. Our speaker today is Shmuel Weinberger from the University of Chicago, and he will tell us about universal complexity. Take it away, Shmuel.
Okay, thank you. Thank you all for coming and accommodating to my incompetence. Yeah, I don't know if I had intended to join the meeting, and in fact, the organizers reminded me to register for the meeting. So I did indeed register for an AMS meeting, and then a week or so later, they contacted me about the abstract. And then it turns out that I had registered for the wrong meeting and that it was too late to register for the meeting. So, I'm really sorry about it. I mean, partially because I spent $300 registering for a meeting that I have nothing to do with. But also I very much appreciate, all of you. You're now, even those of you who I haven't met before, I now consider it, among my friends. I want, by universal complexity, of course, it's not universal in the sense of really, really universal. I mean, it's universal in the sense of this AMS special session on topological complexity. Yeah, so let me just say, topological complexity, of course, is an idea that was introduced by Michael Farber, the gentleman leftmost in the, among the pictures. It was a way of thinking about abstractly what was the problem that, say, people who were programming robots to do. Okay, and it was a measurement of complexity. Let me give an analogy. There was the work of Shannon on communication, where where he invented, of course, information theory, but it's what we now call information-based complexity. And in that sense, I would say that that's analogous to what Michael was doing. He was trying to understand what is the complexity if any continuous function is viewed as completely accessible to you and not complicated at all. Anything you can do by a single continuous function, okay, that's fair game. We imagine that that's doable. Of course, nowadays, the needs of cryptography require much easier sharing of keys and methods of that sort. And for those, we usually use complexity theoretic complexity, by which I mean based on ideas of computational complexity in the Turing model, etc. And, it's a completely different story. So while I'm not critiquing Michael, okay? But I do think that we should be occasionally rethinking the problems that we're trying to do in the study of topological complexity. Now, I know many of you study topological complexity because it's a lot of fun. It's sort of an interesting algebraic topological invariant connected to loop spaces. And the mathematical fun may be, of course, as you make models more complex, you could maybe lose some of the fun. So, I mean, it's a balance, but I still recommend that we try to think about it. Partially, I've listed that I have at the moment two affiliations. The second one is NITMB, the National Institute for Theory and Math and Biology. It's only a 5% appointment, but one of the things that you think about is that locomotion is a problem that all sorts of organisms have to solve. Okay, and of course, organisms don't have access to arbitrary continuous functions, but they do have access to other things, right? Like they have access to randomness that might be provided by their environment, okay, and so on and so forth. Also, they don't have memory. So the current model where we imagine that you know your beginning point and you know your end point And your job is to find the path between them. Of course, if you're a nematode, a worm, you don't know anything at all about that, or a single cell organism. You don't have any clue as to what even the meaning of the endpoint is. And after you've left, you have no recollection of where you've been. Okay, right? So there, the complexity, okay, so I mean, that's a fact. Now, that doesn't mean that that topological complexity is irrelevant to the story of nematodes. Okay, what Michael would tell you is that what topological complexity does is it tells you how unpredictable the route that the nematode will choose if you go ahead and move the food that it's trying to get to, around the experimental apparatus. So it still has an interpretation, but it doesn't have the interpretation that many of us go ahead when we start our talks and we give the motivation for what it is that we're doing, right? I mean, you should realize that, in biological applications, the meaning of certain kinds of invariants are going to be different. Let me just say, I mean, one of the people who I am happy to see is Sasha Dranishnikov. And Sasha introduced some wonderful notion that,
Oh,
that I'm very happy with, that I called analog complexity, and I'm going to later on criticize my terminology, but Sasha motivated it by describing what would be the motion planning that a very advanced terminator would need to do. Okay, which I think it's fine to use that motivation, but nowadays I finally learned, after having been at the NITMB for a year, that maybe you want to describe it as, say, a flock of birds, and that the flock could go ahead and divide up, and you don't particularly care where each individual bird goes, but of course the flock will maybe break up and then move together back later. I mean, so you could give a less science fiction-y version if you're so inclined. Anyway, so let me, at some point I want to talk about math, so let me move in that direction. So let me also mention that the things that I'm going to talk about haven't quite made it into papers yet, but they're all based on conversations with 3 people. So one is Misha Farber, the other is Ben Knudsen. I don't know. And last but not least is Nick Werikow, who I think he's here but not showing his face. Nick is a great expert in configuration spaces and I want to just highly recommend him to everyone. He is on the market this year. So keep your eyes open. Okay, so okay. Hi, Nick. Thank you for showing up and for showing your face now. Okay, so this subject, the prehistory was the work of Shmuel, which was also, it was a matter of trying to inject, this was part of his larger program of trying to introduce topology and geometry into complexity theory. So on the one hand, so there's this Bloom, Cooker, Shub, Shmuel model of computation involving real numbers. And one of the problems that he studied was the problem of trying to solve polynomials, finding roots of polynomials. And of course, what he took for granted was that the output of any computer program that will tell you how to solve, if you give it a polynomial, it's going to have to tell you the roots in some order. Okay, so basically this problem of inverting the symmetric, the thing that mixes things up. I have the function that goes from x to the n mod sigma n, right, down to, okay, and I want to go from x to the n back to there and invert it, right? So it's basically the sectional category of that map. If you like your maps to only be fibrations, you maybe should restrict to the place where the points are different from each other. Okay, so that was roughly speaking his idea, and that it's a very simple idea, and it's not shocking that it's been adopted in many cases. I've already discussed this initial paper of Michael's, where he applied this to the problem of motion planning, but in a pretty soon subsequent paper, he elaborated that this definition has several interpretations. Okay, so So one of them is that I, by the way, discussed. It's the problem about how difficult is it to do the motion planning, right? If you can do a single continuous function, but you can't go ahead, but there's no continuous motion planner, then you have to do something else. So that was one definition. Another definition that he gave was if you're trying to predict what a motion planner would do, how different would those be from each other? Okay. I will not discuss it today, but I think that that second notion has interesting quantitative forms, that are worth re-examining with time. Even though one of the theorems of his paper is that TC1 equals TC2 equals TC3 equals TC4, that all these notions are the same. Somehow, if you first take the notion, take the math and translate it into English, and then you translate it back into math in other ways, you don't always come up with Michael's notion, and that some of these other variants are kind of interesting. I mean, one example to have in mind is suppose you go from S infinity, the infinite dimensional sphere, down to the real projective space. Okay, and you think about that as a problem of you trying to break symmetry. Okay, so we all know that if you restrict that vibration to RPN, you're going to need n+1 pieces for breaking it up, right? I mean, that's the Lusternik-Schnirelmann category of projective space. That's what it boils down to. But in fact, if I ask how many different choices do I have for a section, at no point do I ever have more than 2 choices. Okay, it's just that when I want to describe what's happening globally, if I want to globally describe the sectioning, then I'm going to really need n+1 choices of global things that I do in different places. Okay, but if you just think about the question about locally, how much do you have? Okay, that's just sort of an example of, a way of playing these games, and some of which I think might be useful for other scientific purposes. The other notion that Michael introduced, which basically Sasha and Enkash, not sure if I'm pronouncing the name properly, introduced via the distributional topological complexity, is this kind of random complexity, random motion planners. And so for this one, Michael imagined that you were going to go ahead and, so this is the notion. So let me just say, so Michael imagined that at each point you might have 3 different choices of which route you choose to go from P to Q. Okay, and then your randomness would be you either choose route 1, route 2, or route 3. Okay, however, if you think about, like I said, a nematode in its environment, right, and the randomness comes from the environment, and it uses the randomness, really what happens is that the nematode, there's a map from P to the set of measures on 3 points. So it's really a map to a simplex. Okay, it's not that these things are, are ordered. So that is the difference between what Ben and I call the analog complexity and Michael's notion of topological complexity. We'll see that this comes up when we discuss whatever I called it, universal complexity. But let me just say that I'm not happy anymore with calling it analog complexity. You see, somehow there's one, because this doesn't really capture the difference between what digital computers can do and analog computers can do. It is the case that analog computers like nematodes will choose probability distributions, among different routes, but digital computers can do that as well. You see, I mean, a digital computer, in Michael's version, you flip a 3-sided coin, and then you say, if this happens, you go to line 100. And if this happens, you go to line 200. And if this happens, you go to line 300. But that isn't necessarily what a digital computer would do. I mean, a digital computer could go ahead and take your random number and then operate on that random number, and it would produce something that's more along the lines, it could well produce something more along the lines of analog complexity. Okay, and you would see this if you were trying to actually digitally do root finding. I mean, there's nothing that you have to go ahead and anyway, so let me just leave it there. So I don't know if we're stuck with the terminology that Ben and I introduced, but maybe stochastic complexity would be a better name, but I don't know. But in any case, let me just continue. And I want to now talk about parametrized complexity. Okay, and that's really where universal complexity lives. Okay, so this is the paper. It was a paper that Daniel, Michael, and I wrote, and let me tell you what it's about. And it's really about Roombas. Okay, so again, I don't know everyone here, so I never know if I'm pitching it, telling everybody things they already know, or I'm going too fast. And probably I'm doing some of both. Okay, so here's a mathematical room. It's a square. Okay, and right. So if there are no obstacles, right, it's very easy to do the motion planning. Right, you just do that. Okay, if there's one obstacle, okay, then the problem is, do you go this way around it or that way around it? So for this, the topological complexity, right? It's the topological complexity of a circle. So that's either 1 or 2. Different people normalize differently, so I don't have to worry about getting it right. Okay. When there are 2 obstacles, okay, then it has the homotopy type of the figure 8, as they say, the complement of the 2 obstacles, and the complexity goes up by 1. So far, so good. But then what happens is you tell the engineers that, when there are 3 obstacles or 4 obstacles, it's just as hard or it's just as easy as 2 obstacles. And they think you're crazy when you go ahead and tell them that, because they know that the problem gets harder the more obstacles you have. Okay? You might also tell them other theorems. You might tell them that it doesn't matter if the obstacles are moving. It's the same complexity as if they were motionless. And then they really look at you like you're crazy. Okay. So by the way, so let me just talk about both of those problems, rather than talk about any theorems. Okay. Well, so the first problem I could explain away very easily, and that's the point of the paper that I'm, reminding people about now, about parametrized complexity. The point is that indeed it is true that if you are trying to solve it with 3 obstacles or 2 obstacles, it's just as hard in the following sense. If the Roomba company here's what you would do. You would send it this photograph of your room, including the dog, right? And it would then immediately send you a personalized Roomba, based on the photograph that you sent. Okay, and it would have a chip designed in it that you give it any 2 points, okay, with 1 chip of a certain kinds of expense, right? And the expense would be the topological complexity. It would be able to solve it for any room, and they wouldn't have to charge you more the more obstacles you put in. Okay? Okay, so, right, so there's, by the way, a little miscommunication between you and between the people who are doing topological complexity and the roboticists. The roboticists, when they want to talk about obstacles, they're not, by the way, this paper is about you move the obstacles every day. It's not that the obstacles are moving while the Roomba is moving. Okay, but if you move the obstacles every day, that's what this parametrized complexity are. And you'd like to have 1 chip that every day goes ahead and it looks at where the obstacles are. Okay. Later on, I want to talk about, there's the issue of sensing that is very important in biology and is very important with robots. Okay. But at the moment, we're not imagining that the robot, what's the sensing problem that the robot would have to do? It's somehow, there's some aerial camera that the robot connects to and it sees the entire location of all of the obstacles. But based on that, you would like to know, how much complexity there is. Okay. Okay, and there indeed the theorem in the paper is that as the number of obstacles goes up by 1, the complexity goes up by 1. So every time you add in an obstacle, if you want to have this flexibility, okay, it's necessary to have a more complicated program. Okay, so that was the idea of parametrized complexity. Okay, to capture this idea and for it to be a little bit more informative. Okay, now, by the way, what goes wrong with the moving robots? Well, you see, for us, okay, let's just think about our formulation of the problem. On the one hand, we're supposed to have this omniscience that tells us the position of every object. So in our modeling, if we would be having moving obstacles, what would that mean? It would mean that the aerial camera would be a camera that goes ahead and reads the mind of the dog and tells you where the dog is going to be everywhere during the course of the time that you are moving your robot around. Okay, so indeed, it is true that if you have clairvoyance, that the obstacles that are moving according to known paths within this model where computing any continuous function is one step, okay, the complexity doesn't go up. But if, for example, you don't have this kind of clairvoyance of knowing the future trajectory, and you only know where things are at the moment that you're moving, well, then it's actually, then a lot depends on whether the obstacles can move faster than you can or whether you could move faster than the obstacles. It becomes a much, much trickier problem. Okay, it has some of the same feeling as problems about configuration spaces where you have hard balls as opposed to, where things stop to be vibrations and so on. Okay, very, very interesting questions when you want to actually deal with the moving ones, much harder to model. And I spent many, many, many hours thinking about it with having nothing to tell you about it, other than that I think it's a really cool question, worth studying. But so on. So in any case, let me just point you. So this line was, I think, put in by Michael, that we develop a new approach to the theory of motion planning algorithms. We want our algorithms to be universal or flexible. Okay, that they should be able to function in a variety of situations involving external conditions, blah, blah, blah. Okay. So this has something, so that's really what I want to talk about. How universal is universal? So this is okay, for this example. In general, we want to be having some kind of vibration. I also want to, okay, good. I've gotten it down to lower things. So by the way, so this has had many further developments by lots of people. Okay, and what I want to do is deal with some situations. What do you do when your parameter space is infinite dimensional? Now, I've already mentioned, right? I mean, some of the situations involving, say the analog complexity of finite groups, which were studied by Sasha and Inkosh, and Ben and me. We've already studied some situations where one has infinite dimensional bases. But I'd like to do a little bit more, because I think that sort of probably someone in my extended family wants to watch a movie now. I think that was what just did that come up on your screens too, by the way? No. Oh, interesting. So I didn't have to explain that away. Okay. Okay, so the basic story is that is that we'll be studying, let's see, right? We'll have some parameter space, which is infinite dimensional. And we're interested in understanding what goes on here, right, for the topological complexity. And in a lot of situations, is that the topological complexity in the parametrized sense is infinity. And that feels sad. That feels too qualitative. Okay, so what can you do when the topological complexity when the topological complexity of your problem is infinite? So let me give you an example. of this. Okay. Okay. Okay, so the topological complexity of a circle is whatever it is. It's 1 or 2, depending on your notion. Okay, but suppose that my circle is that. So now to get a family of this, let's imagine that my circle is just the unit circle of a plane. Okay, and the plane is varying. Okay, this isn't, the most universal thing one could imagine, right? But this is a situation, right? So that's a big infinite dimensional family. Okay, and so how could we solve this kind of problem? Okay, so um, so let's just think about this. Okay, so if you have these points, and you imagine that I'm a robot, right? I'm on a robot living on a circle. Okay, and suppose I don't know that this circle is in a plane. I don't, I have had no coordination, right? And I'm told to move somewhere else. Okay, so if the point is not antipodal to me, there's only one thing that I would do, right? Because this circle I'm commenting on, right? It's, it happens to be a linear circle. I've really sensed the whole circle, so I know the distance between any points, right? So there's a new geodesic unless I'm just antipodal. So now if these planes, if these were complex vector spaces, then that would be one algorithm unless I'm antipodal. And then if I am antipodal, then I would then I would just say, I move the circle in the direct, I move from, where I am to I times where I am. And then from I times where I am then to -1 times where I am, right? That would be if I had complex coordinates, if these were complex lines, okay, then I would need just a second motion planner, which is really interesting, right? So here it's a situation where you have the infinite dimensional base, okay? By the way, this isn't an observation that I'm making now. I think it was in our original parametrized complexity paper. But in this case, the base doesn't make it any more complicated, right? If you're dealing with complex, if these were, so to speak, if these were complex lines rather than real planes, or even if they were oriented, right? I mean, if they were oriented, it's the same thing, right? You just go ahead and you move in the direction of the orientation. Okay. Now, what about if it's just a general plane? Okay. Well, in this case, let's just think about it. Choose it. Okay, so I have a point V, and then I always have the antipodal point. Okay, and now any curve I choose is homotopic to, right? Let me just, where am I? Okay, let me just add a page. Okay. Right? So every curve is either homotopic to this one or to that one or to that one, right? They're all they're all, right? The paths that connect them are in a one-to-one correspondence with 1/2 plus the integers. Okay? They never correspond to the number 0, if you know what I mean, right? I mean, so if I had a path, I can always decide what the direction that path is ultimately doing. Even if my path, does something, initially goes, to the left, in the end, if it was homotopic to the one that ended up being, the thing that we think of as being +1/2, I would call that plus, right? So if any motion planner will actually correspond to a section, of that bundle, really of S infinity down to RP infinity. I mean, if you just think about this, what we've done is we've seen that, so that's the proof that the topological complexity is infinite for this kind of unoriented plane bundles. Okay? I mean, right? I mean, I've done it geometrically, but Needless to say, Michael preferred doing it algebraically by his favorite tool, which is heights of, of cup powers of Euler classes or Stiefel-Whitney classes or things like that. And now let me now tell you sort of the general result. And here's the notion of slope. But let me just comment. So what is slope? Okay, so in this example, right, we see that there's an RP infinity involved, right? And if you ask in general, if I had some n parameter family of planes, okay, well, the n parameter family of planes, we know by the CW approximation theorem that, right, first we know it corresponds to a map to some Grassmannian, and therefore it would be living in the n skeleton. And we've computed that the complexity on the n skeleton is about n plus 1 or n plus 2 or something like that, right? So there's a slope that as you're adding more parameters, right, that as you are considering linear planes and you're interested in paths that say avoid the origin, right? Let's phrase it like that, right? In linear planes and you avoid the origin, right? At how many family, how big your family is. There might be some special n-dimensional families that are null homotopic, and you could do it with one planar. Okay, but for the general n parameter family, you need something that's around n, right? Because that's what the complexity restricted to the n skeleton is. Okay, and the result of this email that I got from Misha is that if we were to do the same thing for, no, not lemma 8. Where did this? Oh, here it is, theorem 10. Okay, you could see how well I prepare talks. This is the first theorem of the talk, I guess, but it's called theorem 10, which I hope is very impressive to you all. Right, that if you consider what happens for the Grassmannian and you have a d-dimensional sphere, the slope is 1 over d. Okay, which means that every time that after a little bit of noise for for a point, you of course have the topological complexity of the fiber. So even though it has 0 parameters, right, you still have some non-zero number. But now, as you begin adding more and more dimensions to the base, it turns out that every d dimensions is what requires you to have one more forking in your computer program. Okay? So I think that this is a notion. There are the rough speed. What's the idea? I mean, and I think this is something that we all know, right? That if you have if you have a simplicial complex and you say, look at the k plus 1 cells minus the k cells, oh, that's a 0-dimensional complex up to homotopy. The k plus 2 cells minus the k cells are a 1-dimensional complex. The 2k cells minus the k cells are a k minus 1-dimensional complex. So therefore, when you double the dimension, the stuff in between, so you do the k-dimensional stuff as you will, the next k dimensions is something that deform retracts. You just consider it a new problem, and it deform retracts into the situation that you've already handled before. So this gives you some kind of subadditivity of these notions. Okay, that's what these various lemmas are saying. Okay, I don't expect anyone to read it. I expect people to just follow my hands waving, and I hope it makes sense. So if you just consider how much the complexity is when you restrict to the K skeleton and when you do restrict to the L skeleton, you will see that the complexity for the K plus L skeleton is at most the sum of those two. So when you have a subadditive sequence and you divide by the parameter, you get a slope. So the slope is easily seen to be a number that's between 0 and 1. Okay, and it's a very soft thing, and I think it's a qualitative thing that one would want to know, right? How much does additional flexibility cost you in terms of the motion planning? Okay, because infinity is the most common answer, and I have to say I don't know any, having thought about many examples, I don't know any example where it's like not 1 over d. I think that that's part of the problem with writing this up as a paper. It could in principle be a real number, and you only have it being like 1 over an integer. It's extremely embarrassing as an invariant. But I'd like to, but nevertheless, I mean, if it turns out that it's always 1 over an integer, we'll call 1 over the slope something, maybe marginal complexity or something, and then we'll live with it being an integer valued invariant, and humans seem to be able to live with that quite well. But at the moment, as a slope, we're very anemic on examples. But it's something that I want to proselytize for because I'm a fan of it. And I think that it captures something, as you see in this Grassmannian case. Okay, so now let me move on to universal complexity, right? Which is, suppose that I want to be dealing, where my thing here is an Sn, right? Rather than it being the unit sphere of something linear. Right? I mean, I'm just having this parameter family of things that happen to be the sphere. How in the world would I analyze that? Okay, so the natural way to think about this would be that you would be over B diff of the n sphere, right? The thing that we talked about before, was just the linear version, right? Where we figured it out for BON, right? That's the infinite Grassmannian, and we saw the slope was whatever it was. I guess so this would be BON plus 1, right? That would be what corresponds to the n sphere. Okay, so the trouble with this is that yeah. Oh, and by the way, I mean, and if you would like to, Misha said, how in the world would you ever explain to a roboticist that that's what you want to have? So I said, oh, well, you give the following model. You say that BON, okay, I mean, this doesn't quite work, but you would just say, I have some manifold that happens to be an n sphere living in a Hilbert space, okay? And, I just plot my robot on it, right? I mean, somebody is going ahead and visiting spheres, right? Maybe visiting planets they're hoping to colonize or something. So those aren't bad. Those are 2 spheres, okay? Right, but, and they're completely unparametrized, all right? And then, then you would be, right, because the space of Riemannian metrics is a contractible space. Right. Well, we'll get back to some nuances about such models. Okay. So the good news is, I mean, it's much more classical for the 2 sphere that, diff of S2 is O3. And for the 3 sphere, right, this is a Smale conjecture. Okay. And that, and there's a theorem of Gabai that for hyperbolic 3 manifolds, diff of the 3 manifold is homotopy equivalent to the isometry group. Let me point out the isometry group of the 3 manifold is even a discrete group. It's even a finite group, okay? Which is why this brings in the notion of analog complexity, okay? Especially calculations for finite groups. Of choosing these things, right? So there are some very few cases, right, where you could just go ahead and do it. But the truth of the matter is that by the time you get to S4 or you get to hyperbolic manifolds of higher dimensions, okay, the group of diffeomorphisms or the group of homeomorphisms is a completely, I was going to say it's a completely not understood group, but that's not true. Okay, there've been enormous. But what typically happens is that B diff is going to be some infinite dimensional complex, and something or other about its rational homotopy type is known. It gets connected to algebraic K-theory of spaces. With the concordance stable range, in recent years, there was work of Randall Williams and Galatius, which is extremely deep, and it's about, unstable analogs of K-theory. Fascinating stuff, but way too hard to do. Okay, so that's what I'd like to explain is that, for example, the universal topological complexity of these, right? So this is a circle, this is surfaces, let's say not equal to the two sphere. Okay. For the two sphere, you have slope a half. Okay, because diff of the two sphere is 0.3, and we already discussed what happens for Grassmannians. Okay, and for these, the universal complexity, has slope 1. Okay, so the universal complexity is infinity, and it has slope 1 for every surface. But for hyperbolic manifolds of dimension equal to or greater than 3, there exists infinitely many manifolds whose universal topological complexity is bounded. In fact, I think it's equal to the topological complexity of the manifold. Okay. But certainly not always. Okay. So this is one point. This is the other one. And then the open problems well, of course, there are infinitely many open problems, okay, in this subject. But one of the open problems is to characterize when the universal topological complexity is finite. And I will just say that the obvious conjecture is false. Hopefully, there will be an obvious conjecture after I explain the other results. Okay, and that slopes, etc. Okay, those, that even when it's infinite, I think the slope is an interesting question. And what I think is that the way one's going to figure out about universal topological complexity, it will correspond to understanding the universal topological complexity if you study let me say, metric graphs up to isometry. Okay. Yeah, right. That I'm not going to be looking at families of metric graphs where the metric is actually changing. I'm going to look at families of metric graphs where all of the edge lengths are fixed to be the same. Okay, so that's the rest of my talk, which should be 17 minutes or 12 minutes if I'm going to allow 5 minutes for questions. Actually, are there any questions at this point, by the way?
Can I check the definition of UTC? Is it so you have a space X and then you look at the homeomorphisms of X and then
Right.
you take the associated fiber bundle with fiber
Right.
X and then you take its parametrized TC?
Yes, that's all I mean by the universal one.
Okay.
Right.
Thanks.
It's the one that for any fiber bundle would be related to that. Okay.
Yep.
Okay. And okay. Yeah. So okay, so let me just sort of make another remark. Okay. Which is, I hoped this would have something to do with sensing. Right? That I would be that, for example, suppose M is a manifold that has no finite finite transformation groups. Okay, just to organize your thoughts. Okay, there are such manifolds. They weren't, I think they were discovered in the 1970s. I think it's a paper of Connor, Raymond, and Weinberger, where the Weinberger is not me. Okay, so there are such manifolds, and for manifolds like that, you could think about B diff of M, right? The universal one. This is equal to the space of manifolds in the Hilbert space, that are diffeomorphic to M. Okay, right? That if I have M, it has a unique thing up to isotopy, etc. And I look at the metric, there will be a parameterization. If you like, diff M acts on the Riemannian metrics, and we're assuming that the Riemannian metrics are a nice contractible space. Okay, and and this is telling you that there's no isotropy. So this is a very good model. Okay, and in general, so what you could imagine is if I were to put on such a thing, and I want, right, suppose that my basic algorithm was given 2 points, I want to choose the geodesic, the shortest geodesic connecting one to the other. So on a Riemannian manifold, that's a motion planner that works for almost every pair of points. I mean, it's really not bad. I mean, it's just that it's discontinuous when you move through the cut locus. Okay, right? So that's why you typically need more. Now, if I just have a manifold, finding the Riemannian structure, that's going to take a lot of exploration. So it depends on my sensorium whether I could do it. But now, suppose that I'm just dropped on a manifold, and the manifold does have a symmetry. Okay, right? Suppose I'm dropped on the circle, and I'm a symmetric robot. Okay, and the circle has a symmetry, and I'm told to go to the antipodal point. There are 2 geodesics. This is, whatever, I forget that classic analogy of the donkey that dies of starvation between 2 bales of hay that are equidistant. Right, that would be my situation. There does not exist a solution that maintains where all that I'm allowed to do is invoke the sensorium, right? This is that measure 0 occasion that just is, that when we're talking about, and in some other models, we would solve by flipping a coin at this point, right? But if you're trying to do it deterministic, there's just no way to do it. Okay, so that's sort of, that's sort of a little bit of a funny aspect, right? So this is a good model. The space of manifolds, say stuck in some Hilbert space, use Nash embedding so that you could get any metric you want as being the induced metric, blah, 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 that are diffeomorphic to M and have no symmetry. Okay, it turns out that having a symmetry is an infinite codimension condition, except in some low dimensions. Like the circle, every metric on the circle is just the standard metric on the circle up to rescaling, after you apply the action of the diffeomorphism group. Okay, the circle is a little bit anemic, but when you go to higher dimensions, then having any symmetry is, right? Having a symmetry is deadly for the most naive point of view on how you're going to solve the problem. Okay, and having no, but it's not necessarily a problem, right? In order to make this a well-formed problem, right? That when you have symmetry, it's not reasonable to expect that you'll be able to do it. So then we would imagine that your universal problem is, I have this guy, I'm just plopped on it. It happens to be diffeomorphic to M, and I want to do motion planning that way. Okay, that's the way you should interpret it. Okay. However, okay, so somehow that's I think the way, right? So so even though if you were dealing with a hyperbolic manifold, what I'm telling you is your hyperbolic manifold has some symmetry. It's in fact the most symmetric metric. You can prove that any finite group that acts effectively on a hyperbolic manifold also acts by isometry on any metric, on the hyperbolic metric. Okay, it is the most symmetric of all metrics. Okay, and here is sort of the proposition, which is that the universal topological complexity of a hyperbolic manifold is equal to the parametrized topological complexity of, over B isometries of M. Okay, you look at okay, so maybe I should even okay, so let me just right, so let me just the isometry group is inside of the diffeomorphism group, right? So this is the M bundle, right? So obviously, there's some inequality this way. Okay, but the statement is that this is an isomorphism. And what is the proof? It's less than a line. It's the homotopy invariance of TC. Okay, so we all think about TC. You're given a pair of points, you find a curve, etc. Okay, and from some geometric point of view, and certainly if you think about your, from a very differential geometric point of view, right, the fact that it's homotopy invariant is not obvious. Okay, the proof of homotopy invariance, when you give the right definitions, is just an application of the homotopy extension principle. Okay, so the real point is that even though you're using B diff, you could really go ahead and use the monoid of self-homotopy equivalences and use vibrations and all of those things. So the real point is that even though we don't understand the diffeomorphism groups, and if you're thinking about this as a geometric problem, okay, which, by the way, or maybe I'll say an open problem is, okay, how to connect this to sensing. Okay, I think it's easier to say it intuitively than precisely. Okay, but the basic point is that for the purposes of computing parametrized topological complexity, you might as well work with vibrations as opposed to working on the manifold. Or another way to say this, which I don't advocate, is if I take the manifold and I cross it with Hilbert space, and I consider homeo of M versus homeo of M cross Hilbert space, homeo of M cross Hilbert space begins, is more of a homotopy functor than M itself, or maybe the Hilbert cube. Okay, so you don't do the motion planning on M, you do on M cross the Hilbert cube, then homeo of M is no longer as mysterious. But it's much, much better to just think about this as being, systematic application of the homotopy extension principle. But now if you think about it, right, this doesn't tell you at all. I mean, just think about what you would be doing. If I have a manifold, right, which happens to be a metric on a torus, how do I find the map to the torus? Right, because I'm really supposed to, right? I mean, I want to be doing motion planning on this manifold homotopy equivalent to a torus. Okay, so I might need, in the case of the torus, I might have to have a few, I might have to mark the fundamental group in some way, right? So what would I do? I'd find some differential forms. I might go ahead and say the differential forms I'm going to do are going to be harmonic. And that will build for me the homotopy equivalence from the manifold to the torus. Then somewhere or other, I'll say, well, but I really need the homotopy inverse because I'm going to have to be pulling back curves. And well, the space of homotopy inverses, well, that's contractible, so it doesn't bother us. As a homotopy theorist, it doesn't bother us. If you actually want to understand all of these things that we're proving exist, I think it's extremely mysterious. Oh, anyway, alas, my time is almost up. So let me just comment that when you do this, this total space that you look at it's really the following bundle. So if the isometry group of M acts freely on M, okay, then the vibration one cares about could be identified with M cross M mod G. Okay, this is a drop tricky, but this is what the bundle ends up getting pulled back from. In the situation where the isometry group is acting freely, which, as you could see, this is a hyperbolic manifold of dimension n, and this is one of dimension n, so the whole thing is at worst 2n, and there's the theorem of Sasha. I don't know if you had a co-author, that the topological complexity for hyperbolic manifolds is in any case twice the cohomological dimension. So so there's no room for anything to get very complicated. Okay, so this is why the universal topological complexity is finite, because the whole situation becomes equivalent to a finite dimensional bundle. Okay, it becomes much more interesting if G acts non-freely. Okay, so if G equals ZP, okay, and suppose that, so here's M, and suppose that you have a ZP action and it has two fixed points, okay, and actually has two components of fixed point set. Okay, I would choose the nearest points to one from each cover, and then there would be, sort of P shortest geodesics connecting one to the other. Okay, and I'm now going to not solve the general motion planning problem. I just try to move from this point to that point. They all have well-defined names in terms of the manifold, right? So I know what I mean, for any, right, for, all of these embeddings as I'm looking at this M family, I just want to constantly over BZP, right? Just restrict my attention to that BZP, and I try to move from one to the other. Well, this is exactly what was called the analog complexity of BZP, which Sasha computed that for lens spaces, it's exact, I mean, oh, well, it's not exactly the same. It's the same calculation. Okay, it's the one that we did before of S infinity down to RP infinity. So this has slope 1. Okay, and in fact, for any P group, if you were to be having a disconnected fixed set, the Sullivan conjecture could be applied. I don't think it needs the whole force of the Sullivan conjecture to go ahead and get that you end up having infinite complexity. So you now might imagine, so it's sort of very interesting that even though you're looking at the space of bumpy metrics, the metrics that are not themselves hyperbolic, everything results from analyzing what the isometry group is and how that group acts on the manifold. So what's kind of a little surprising, and this is related to the analog complexity problems, is that suppose that you were to have the following situation. You have a group Z6, and you have two fixed points for Z6, right? But if you look at the shortest geodesics connecting these 2 points, there are 5 of them, 3 of them permuted, but and the way Z6 acts on it is by permuting these 3 with a Z2 kernel and these 2 with a Z3 kernel. Okay, so if you were in a situation like this, which is pretty, I agree it's special. This is another situation where the universal complexity is still finite. Okay, this is related to the counterexamples of the beautiful conjecture of Sasha. Sasha conjectured that the analog complexity of a finite group was the order of the group. And this was that, if this was a P and that was a Q for ZPQ, this one had the analog complexity being, slightly bigger than the larger of P and Q. Okay, so this is related to that. It's the same phenomenon, just hidden. I know I didn't really explain things. I'm blathering in these last minutes, so it would probably be better if I stopped. But in any case, you might have imagined that the question is, would you know how to go ahead and do it on the hyperbolic manifold itself? And that when you're disconnected, you would feel that, oh, I want to be on the singular set, and there's no way to do it in the singular set for this case. But the answer is no, that isn't the correct analysis. So I mean, I think that this really involves understanding the theory of homotopy fixed sets for non-P groups. For P groups, you have the Sullivan conjecture, but for non-P groups, I don't know the theory. I'm sure that a competent algebraic topologist could set me straight. And I think that in order to figure out what goes on for hyperbolic manifolds, these are the kind of very simple pictures you have to draw. You're looking at combinations of geodesics, and that gives rise to some kinds of graphs, and you want to play around with those graphs and understand just sort of the isometry groups of those graphs, that universal family. I think if you would figure out when that has finite complexity, then you would be able to do hyperbolic manifolds and very many k-pi1 manifolds. I mean, if you look at this, the proof didn't really use hyperbolic manifold. It really uses k-pi1 manifolds where the group pi is centerless. Okay, I mean, if you want to have precise measurements, then you need to know about the poset of abelian subgroups or something like that. Anyway, I've talked too long. In fact, indeed, I did talk a minute over time. So I apologize for that, and I am done. Okay, thank you.
Thank you, Shmuel.
Okay, thank you.
Are there any questions? I guess silence means no.
Okay, I will interpret that as was so clear and that I asked you guys questions.
I could ask something
Yeah.
just about the last example with the 5 or 6 points joint.
Yes.
I mean, what is the space?
Oh, what is the manifold? I mean,
yeah.
So I can't swear that I know that they're the hyperbolic manifold that realizes this configuration. But
What do you mean by that?
Well, I mean, the way I described it, that I would want there to be, a Z6 action that has, 2 fixed points for the Z6, and that the configuration of shortest geodesics connecting those 2 points were exactly this. I mean, I could really do it with, some kind of aspherical polyhedral complex where I have some more flexibility to build it.
Right.
So the truth is that the whole time I've been saying hyperbolic manifold, but most of the time I didn't really need the full strength of that.
You want some sort of configuration of the fixed point set and GD6 between them. Yeah, okay.
Right. Yeah. So the key point is that you look at the isometry group and you look at the orbifold, the E bar gamma associated to the orbifold extension, and it's, and you want it to have a metric of a certain sort. But for the flavor, I mean, a lot of it is much softer. And what I really think is that, even though I said that the interest, I mean, if you're thinking about it from the point of view of sensing, you don't want to be looking at the symmetric objects. For a lot of these problems, you look at the symmetric object after all, even though it has a much less plausible robotics application, right? I mean, that I would not be given the graph. I'd be given the graph as an embedded object in Hilbert space or something like that. But, we don't have trouble about just thinking abstractly. We have the isometry, whatever, we have this contractible space, etc. You just form that vibration and, and analyze it. And so I just think that if you take, say, just working out the one-dimensional theory. So the one-dimensional theory is literally, I just have a metric graph, a finite metric graph, which has a non-trivial isometry group, which is finite. Don't tell me the circle, make it a genuine graph, it has vertices, edges, isometries are only allowed to take vertex to vertex, etc. So the isometry group is finite, and just consider, that, B isometry group of that, and you're looking at, the parametrized complexity of that universal family of that metric graph. Okay. And I think that a complete analysis of that should ultimately lead to the complete analysis for, say, at least, what the universal theory for manifolds that happen to have non-positively curved metrics on them. Okay, well, or at least negatively curved metrics. Non-positively curved, you have to also work out the theory of the torus, where they're center. But, all right.
Any further questions? I'm going to go ahead and stop the recording now.
Okay.
Thanks again,
I beg
Shmuel.
people to give some more examples of slopes. I'd like to see a slope of 2/3. I'd really like to see the square root of 2/2. Better would be pi minus 3. There are more and more, exciting numbers out there.
So apparently there are lots of questions.
Yeah, no, there are tons of questions, but I'm the one asking all of them.
Yes.
Yeah, no, I think that there,
All righty.